think I gave one to everybody. So magnetism is one of those things that I would guess everybody has played with magnets at some point. And here it is. This is magnetism. I've got two magnets. I can do that, and they're attracted to one another. And I can also turn this one around, and I can push that one with it. It's just like magic. So here's the definition: of phenomenon causing attractive and repulsive forces between objects. This is the part you're probably not aware of. It's relating to motions of electric charge. So inside these magnets, there's some kind of motions of electric charge moving around. Did you know there's anything electrical going on inside a magnet? How about inside my pencil? Anything electrical going on in there? Anything with charges inside this pencil? Yes, what? Not everything. There are three kinds of particles in that pencil on an atomic level. Two of them have charges and one of them doesn't. What's something that's negatively charged in my pencil? Electrons. Positively charged? I know, but what are the positively charged things? Protons, and then there are neutrons that don't have a charge. So even though it doesn't seem like there's anything electrically going on inside a pencil or inside here, there are electrons moving around in there. It just so happens that in a magnet, the way those electrons move around is more kind of orderly, and it causes this magnetic force to occur. And actually, I would say there are magnetic forces in here, but they're not all working together, so we can't sense them outside that pencil, but they're working inside the pencil. We'll come back to that at some other later point. Okay, so magnetism is this either attraction or repulsion. And you just have to trust me that it's caused by motions of electric charge. We'll come back to it. So, Kevin, stop working on that. Just focus on the notes. This is the North Pole. I don't even really know which one is north, but I'm going to figure it out right now. The North Pole of the magnet is the pole that tends to point itself toward the Earth's current North Pole. So, as I was saying earlier, the red side of this compass is a magnet, and the red side is the North Pole. And I know that because it points north. That's the whole point of a magnet. So, if I can figure out, like with this, it seems to be attracted to this side of my magnet. So if north is attracted to this, what is this? I'm jumping ahead, but it's south. Let's jump to this. As with electric charges, opposite magnetic poles do what? Do they repel or do they attract? Opposite poles. They attract. Opposites attract, and like magnetic poles repel. So if I can find the pole of this magnet that is attracted to that red, it's not this one, it's this one, then this must be the south pole of this magnet, and over here on the back, that must be the north pole of that magnet. Ooh, let me focus. All right, so the definition, the whole idea of having a north pole and a south pole on a magnet, that came from this. Long time ago, people made basically a compass, and the side that always pointed north, they called the north pole of the magnet. I'm not actually sure if the magnet got its name first or the north pole of the Earth got its name first, but the north pole of a magnet points toward the north pole of the Earth, which is actually the south magnetic pole of the Earth, if you think of the Earth as a magnet. So south pole, it's the pole of the magnet that points toward the Earth's south pole. And that's the side of this that's either blue or green. I can't really tell what color it is. I guess it's blue. All right, magnetic field lines. They're arrows pointing away from the North Pole toward the South Pole. This says draw some of these on the Earth to the right. So they would look like this. Magnetic field line is going to come out of the North Pole and go into the South Pole. And they'll actually go all the way around and then connect with one another. So they go like this. And these, help you visualize how magnets are going to interact with one another and how magnets would interact with other things. So I could draw more arrows coming out like that and more arrows coming in like this. You're right, A12, since that's this class. So this is the magnetic field. The symbol for this is a letter B, capital B. So if I write B here or B right here, that just tells you that what this arrow means is it's the direction of the magnetic field. And it always points from north to south. All right, draw some bar magnets sticking together end to end. I might have, I think I've got some bar magnets down in this. Oh yeah, a couple of them. So I can stick these together different ways. This is going to maybe make a mess on my desk. They don't look like they want to go together like this, so maybe this will work. Maybe this will work. Maybe this will work. They don't like any of that. How about, ooh, they like that. They like this. Okay. Finally found the correct orientation that they like. So if I'm going to draw this and do some labeling, this is the end-to-end part. I guess I don't really know which is north and which is south. I could figure it out with this. So somebody tell me, this end of this magnet, is this north or is this south? Well, that red is the north, and it's pushing it away, so this must be north too. And if I go to this end right here, and wait for everything to stop wiggling around, the red is pointing at it. So if this is north, then this is south. So that's how I'll label it. So this is south, north, and if that's north, what's this? South. And if that's south, then this is north. Now I can also put these magnets side by side. And if I do that, if I have one like this, south, north, what's going to want to be right here? You think so? Let's try this. So let's just say this is south, this is north, this is south, this is north. So can I, yeah, that works. So if I have it like this, south, north, I can take this south and put it next to that north, and they're happy that way. So they stick like that. So I've done number 3, I've done number 4, and then number 5 is just really the same thing, but it's saying show how their magnetic field lines align with one another. What I haven't read is another way to think of magnetic attraction and repulsion is to say magnetic fields like to match up with one another, go in the same way. So here's what I mean by that. If I draw a magnet like this, south, north, and if I were to draw the magnetic field lines coming out of this, they would look like this. The field would be coming out of here and going into there. So if I take another one of these and I put it down here, then these things that are coming out this end would be going in that end. So it would look like just like what I just had, except now I have basically one big magnet. And one thing I don't have here is iron filings. Has anybody ever seen a teacher play with iron filings and magnets? If you sprinkle a bunch of little tiny pieces of iron all around here, the iron will make these kinds of patterns. So that's the pattern we get if we put these two end to end. The magnetic field that comes out of this one really goes right into that one. We could continue drawing it here. And then it comes out of here and goes back in south. So field lines go into south and come out of north. And then if I drew this and tried to draw the lines for it, it would work too. This is south, north, north, south. So the magnetic field is going to come out of this and go right back into that. And it's going to come out of this and go right back into that. So this is what I mean by aligning with one another. The field lines are doing just what they would ordinarily want to do for both magnets. And they like that. I'm not going to have you draw this on a test. I would expect you to be able to draw something like that on a test. If I just said, you've got a couple of magnets that I give you, south and north, north and south, and you put them together, show me how they might match up. You can either draw this or you can draw that. I don't think I'm going to have you do this, but this will help you understand some of the other stuff we'll be seeing. If anybody has questions, you just jump in. Now, how are magnetic fields created? I mentioned that it was because of moving charges, and I'm going to create a magnet using this this wire that's wrapped around the compass. And I've got a lot of other magnetic stuff around here. My computer, these magnets, probably a bunch of other stuff that's creating magnetic fields also. So all those things are maybe going to interfere with this a little bit, but it'll still work. So there's this thing called the right-hand rule. You've got a pencil in your hand, so grab your pencil like this. With your right hand, just grab it like that, a big power grip. And then take your right hand or right thumb and point it along your pencil. So the way this right-hand rule works is, if you do this, it's got to be with your right hand, doesn't work with your left hand. If the current is flowing the way your thumb is pointing, this way, then the magnetic field is going to swirl around the way your fingers are curled. So if current's flowing through my pencil like this, if my pencil's a wire, I point my thumb in that direction, curl my fingers around it, that shows me the magnetic field. Now if the current's flowing the other way, I take my right thumb and I point it the other way, curl my fingers around it, and that shows me the direction of the magnetic field. So I'm about to make a magnetic field using one of these batteries. I'm going to connect this up, and it'll be more interesting if I do this. So look at the way north's pointing right now. Now as soon as I connect this, see what north did? And I disconnect the battery, does that. So the magnetic field is right now, it's going to the left here, it's going this way. If I disconnect it, then it's not. Guess what will happen if I flip the battery over and I have the current go the other way? Guess which way the red's going to point? Any guesses? Here we go. Now the red points to the right. So when the current goes through one way, the magnetic field is rightward. If I flip this over and the current goes through the other way, the magnetic field, hard to do. I should come up with a better thing. The magnetic field is, I must have not reversed it. I must have thought I reversed it. Yeah, the magnetic field is leftward. So here's the way to understand how a solenoid works. This is a solenoid, not the compass, but the winding of all this wire around it, the wire that's in a coil. A solenoid is a coil of wire through which current is flowing, and the right-hand rule can be used to understand the direction of the magnetic field if we know the direction of the current. So if you look at this hand right here, sometimes it helps to use a piece of tape. So if I've got this piece of tape, and I've got my hand over here on the right, and according to the diagram, current is flowing this way along the tape. What I do with my hand is I take my right hand, I point my thumb in the direction of this current, and then I curl my hands around the wire. But since there's so many wires, I can't really curl my hands around it like that. I can just stick my fingers through it. But look at the direction my fingers point. They point through the tube to the left. So in this case, B, which is the magnetic field, is going through the solenoid like that. So here's some practice for you. See if you can figure out if current is flowing like this, it goes through this wire, goes back behind this cardboard tube, comes around the front like this, goes around, and then comes out like that. Which way is the magnetic field? Is the magnetic field going to be going up and to the right, or is it going to be going down and to the left? See if you can visualize that. Or, get something in your hand. I've got a bunch of tape rolls. If you want to borrow a tape roll for this, all you ever have to do is draw an arrow on it, get it pointing the same direction as these arrows, grab the tape roll with your right hand, point your thumb along, and then see which way your fingers curl. So does anybody have an answer here? Does this is the magnetic field going to be going down and to our left, or up and to our right? (50-50). All right, well, watch me. Maybe as soon as you think you know the answer, tell me. So I've got my tape roll, and I've positioned it just like this, with this current going around like this. On the near side, it's going down. I want to take my right thumb, point it along here, and then stick my fingers through the coil. Which way are they going to go? Are they going to go up and to the right, or down and to the left? This is my right thumb. Anybody, can you anticipate at this point? Okay, so in order to do this and keep this thing where it is in your field of view, I've got to sort of turn my body around. There's my right thumb. It's pointing in that direction, and when I curl my fingers through, they go through like this. So my right thumb comes across the front, fingers curl through that way. Which way does the field go? Up and to the right, or down and to the left? That way. So the answer is like this. This is the magnetic field. That's B. Or B. It's going through this way. How about this one? Now the current is going around the back of this, coming across the front this way. Any ideas? Which way is the magnetic field going to go? Is it going to go to our left or to our right? Left? Let's see. So if I simulate this with my piece of tape in my right hand, do I turn the tape like this or like that? Which one? Does the arrow, should the arrow go up on your screen or go down on your screen? I think I need to call on people. Nobody's answering. Get my popsicle sticks out. All right. Scott, you've been called on. So tell me how to orient my tape roll to make it like this. Do I have my green arrow pointing up across the screen or down across the screen? Which one would make this tube like this tube? Down. Okay, there. All right, now, next person's got to tell me what to do next to figure out which way the field is going to go. Isha. So what do I do? What does this arrow tell me? What part of my body should be like that arrow? Which thumb? My left thumb or my right thumb? My right thumb. So I need to turn so my right thumb is going just like that arrow. And the next person, Isabella, you get to answer my next question, which is, now that my right thumb is going in the direction of this arrow, what do I do? I'm trying to figure out which way the magnetic field is going to go through this tube. Is it going to go left or right? And the first step is to think of a tube where the current is coming down across the front. Second, line your right thumb up with that current. And then third, what do I do with my fingers? I curl them around the wire just like this. So I'm grabbing here and I curl my fingers around the wire. Now look at my fingers. Are they pointing through the tube to our left or to our right? My fingers are going to the right. So the answer is, this is B. That's the direction of the field. And then one last one. I'd like everybody to try this. See if you can do this one. And I'm going to come by, and I either want you to have, an arrow coming out the top saying B, or an arrow going out the bottom saying B. One of those two is the direction of the field. I want to see if more of you can get it right than wrong. But let me think about it myself. Okay. Got it. I'll give you a little more think time, and then I'll come around. So this right here, you've got to have an arrow either coming out the top or going out the bottom. What's it? Yeah, I'll come around and check them.
I didn't write it, it's just at the bottom.
Just draw it out. I'll tell you what it's at. I'll tell you what it is. I don't want to give anybody any hints who haven't checked yet. More people have gotten it right than wrong.
It's fine.
So point. Point. Just show me the direction. Xander, do you have it?
I don't have a pencil.
Just point then. So it was, let's see, 8-4 in the more of you got it right than wrong. So the answer is this way. So to make it a little clearer, the current's going to go across the front like this, and then eventually out that way. It's going around the back, but it's going across the front that way. So if I take my tape roll and I do this with it, and I put my right thumb pointing this way and curl my fingers through, then they go like that. All right, so these, see how you can do on these. These are the same thing, except you're given different information. So here we have the field, which is the direction of fingers, and you just have to figure out which way your thumb points and therefore which way the current is going. So I'll do this one. So if I stick my fingers through like this on my right hand, and then I grab this and I curl my thumb around, my thumb points to the right, which tells me this goes to the right. So where does this current go into the loop? Does it go in at the top end, or does it go in at the bottom end? Which one's going to make it come around the front, going to the right like this? Where does it enter this loop? Is this where it enters, or that? Anybody know? The bottom, yeah. So the current is going to go in here, and it's going to come out there. So see if you can do that for these two. See if you can figure out, based on the magnetic field, which is the direction your right hand fingers would go. When you do this curling thing, you can figure out the direction of the current through the wire. Does anybody want a piece of tape, a roll of tape? It's kind of a nifty tool. Actually, I don't know if it would help you as much for this. For this, you just stick your fingers through. All you got to be able to do is imagine shoving the fingers of your right hand through that tube in the direction shown. And then you just grab onto the tube and look at which way your thumb's pointing. So I want a show of hands for this in just a minute, this top one. All right, so raise your hand if you think that the current enters this wire right here. Raise your hand. If you think the current enters there. Raise your hand if you think the current enters here. So it's, now let me try. So here's the tube. I stick my fingers through with my right hand like this. Oh, sorry. Can't even really see that. So I stick my fingers through like this. I grab and look at my thumb. It's going down across the front. So it's going, current's going like this, which means it's going to come out here and it's going to go in there. So nobody had it right. Everybody who guessed was wrong. Now this last one, see if we can do better on this. As a class, that was pretty bad. I think what I'm going to do when we have a quiz over this is I'll have maybe 3 questions or 4 like this, and if you get them all right, you get bonus points. If you don't get them all right, nothing happens. So if you can get good at this, you have an opportunity to get extra points, and if you can't do it, it doesn't hurt you. So see if you can do this one. Figure out where the current enters and where the current exits. You just got to think, if I stick the fingers of my right hand through the tube this way, and then I grab on, which way is my thumb pointing, and that'll tell me the direction of current, at least on the near side. Okay, how many people think the current enters the wire here? Raise your hand. 2, 3, 4, 5. How many people think it enters the wire at the other end? Raise your hand. 2. So more people got it right than wrong this time. If you stick your fingers of your right hand in here, and then you grab, your right thumb is going to be pointing like this. So the current enters here, and then it exits. Maybe I said this wrong. It exits there. So it'd be like this. I stick my fingers through here, I grab, and you can see my thumb points down across the front like it does in the picture. And since it goes down across the front, the current's going to come out there. Let me quickly jump to the assignment, or the next project. I know I've been over this, but I just want to reiterate what to do because I think some people have forgotten. If you have no idea how the solenoid buzzer works, you should watch the video again. Either watch it during class or watch it at home. If you kind of remember how it works, then you ought to be able to just use this diagram that I made and read the directions here. Here's the diagram. The pieces of wood, I've got 3 pieces of wood here. They're hot glued together. If you're going to do this like I did it, you can't stick this nail through the wood after you've hot glued them together. So you would need to assemble, you'd need to think about how you're going to assemble this. So the way I think I did it is I drilled a hole in this piece of wood, I drilled a hole in this piece of wood. I made sure that those holes were going to be lining up with my flexible piece of metal. I made my solenoid. I screwed in the metal. I inserted my solenoid into this wood, and then I hot glued the wood on. Then I hot glued this wood on, and I pushed the nail in with the bared wire touching it. I don't know if I already mentioned this, but I screwed in the flexible metal with a little bit of the solenoid wire wrapped around that screw. So when this is all done, and I connect this to a power source somewhere between 3 and 6 volts, the electricity flows through this coil of wire, and if it flows over the top, then it would be like my thumb's pointing over the top, my fingers are going left, so this would be a magnetic field going to the left. Doesn't matter, either way it's going to attract this flexible metal, and as soon as it attracts it, it pulls it away, breaking this connection and making the circuit stop. So in the beginning, electricity can flow through the solenoid, through this screw, into the flexible metal, into the nail, and back to the battery. But when the flexible metal moves over, that all stops. So the solenoid lets go and the flexible metal pops back.